Professor Zhan Shi from the University of Paris, one of the leading researchers of this very well-known center, probability center. And we asked him to say a bit about Paris 6, about the principal themes, the directions of research, and so on. Albert Nikolaevich also asked me to ask Zhan to do this.
So you are in Paris, but not in the China.
I'm a Chinese citizen.
Are you wanting to know about Chinese scientists?
I thought that you are directly from China.
I am from China.
Where did you get your education? In China?
Yes, I got my undergraduate education in China. So I come from the university in China called University of Science and Technology of China. And that's what there's no hope at all for the university.
How long you are staying in the Paris?
So I went to Paris for graduate study in '86. Wow, so that was 27 years ago. So that's where I got my master's degree and PhD diploma. And then I spent 2 years as a postdoc in London. And
How long is it?
un petit peu, c'est ma langue de la vie quotidienne.
Parce que because we have many people who can.
Sure, yes, and there's quite some people in the audience actually in Paris, and of course, so certainly we speak French in private.
Okay.
Okay, thank you.
So, go to your scientific.
Thank you. Okay, so I don't need to do any advertisement for my university anymore. Yes, I guess. Okay, so first I wish to thank Professor Koneker for the kind invitation. It's a great honor for me to be here doing mathematics with everyone. So I wish to study together. Branching random walks. So it's based on some exercises which I have learned from A.D. and we are using both in Paris. So maybe let me start with a simple example. Okay, I'm afraid I'm not able to reach the upper parts, so I'm going to waste most of the space here. So I'll start with a simple example. So branching random walks, from its name, I guess everybody realized that it's a kind of random walk. It means that it's sums of ID random variables, but with a branching mechanics. So it's at the same time a random walk and it's a branching process. So maybe I will make a parallel table between usual random walk and the branching random walk. So this, on the right hand side, is an example of usual random walk. On the right hand side, I will present an example of branching random walk. Oh, by the way, so everything is one-dimensional in my case, and time is discrete. So it's really the easiest setting you can imagine. So one-dimensional random walk is just sum of I random variables. So this is time, this is space. So at the beginning, I have a sequence of independent and identically distributed random variables. I will call them psi I. So they are I, independent and identically distributed. So my random walk starts, let's say, at the origin, and at time 1, so after a unit of time, it's going to make the first move, and the size of the first move is the value of this psi I. So in my picture, the value of psi I is negative. And then in the second time, the movements, the size of the movements is psi 2. So the value of my random walk at time 2 is just psi 1 plus psi 2, and as you keep going. So at the end, you'll get something like that. So that's probably one of the fundamental settings you can imagine in probability theory. And now, with branching random walk, so it's still the same picture, but except that you have, moreover, a branching mechanism. So let me make a picture. Again, this is time and this is space. At the beginning, I have just one particle represented by a cross here at the origin. At time 1, it's going to make a jump, and each time the jump size is according to a probability distribution. Again, there is a probability law that governs the distribution of my branching random walk. But except that now I need to take into account of the branching mechanism. So now I have 2 particles at time 1, let's say. Yes. So I'm going to do like this. So in my picture, these two, the two sizes are independent copies of the random variable psi. So I have 2 independent random variables. They are independent, and both of them are distributed as the generic random variable psi. Yes? So that's the situation at time 1. At time 2, each of these particles is going to be split again on their turn. And each time the jumping size is distributed as psi, and all these jumping sizes, all these jump sizes are independent of each other, and so on and so on. And I'm not going to make any more picture because after n moves, of course, the number of particles is 2 to the n, so it's going to be to increase very rapidly. So this is the case of branching random walk. I guess at this stage, I guess the definition is perfectly clear, right? There is nothing very special about this. Okay. For the usual random walk, a classical assumption is that you assume, maybe I write here, something. Classical assumption is that you assume that psi has mean 0 and the variance is 1. As long as all the psi's have finite second moments, you know that you can always bring back to this particular situation, because otherwise all you need to do, if it's not true, all you need to do is to define a new sequence of random variables, psi q, let's say, which is psi I minus the expectation, and divided by the standard deviation. So as long as the psi i's have finite moments, and it's not just a constant, which is 0 because I assume that expectation is 0, then by this simple linear transformation, you can always assume that the expectation is 0 and the variance is 1. That's trivial, yes? There is something similar for branching random walks. There is also a standard assumption when you work with branching random walk, except that now the assumption looks a little.
So that you have to write the variance.
Oh, yeah, I need to write the variance, you are right. Otherwise, I have some trouble. Oops. Now I think I'm safe. Thank you. So the standard assumption for branching random walks, if you have never seen it before, then it might look a little bit exotic, but in reality, it's exactly of the same nature. So now the assumption, which I write here, the standard assumption, I'll give it a name, call it assumption star. I write it a little bit differently. Let me sum over the two particles on the first generation. And, okay, I need to give the value, okay, I need to give the value of a branching random walk. So if this point, I'll call it x, then the value of the branching walk at this point, I'll call it v of x. So v of x is x branching random walk. So which means that when in my picture x is in the second generation, so the value of v of x is this value plus that value. So it's the sum of two independent random variables, both distributed according to the law of psi. I hope the definition of v of x, I hope it's all right. Yes? So now, the first part of my assumption is that I look at the exponential to the minus of my branching random walk, and I sum over the two particles x on the first generation. The absolute value of a particle here, it just denotes its generation. So in this sum, I have two terms representing the two particles in the first generation, and I look at sum of exponential to minus the value of the branching random walk, and I assume that this expectation is 1. Of course, if you don't...
What is v? What is v?
That's v is the value of the branching random walk. So
what is x and what is x?
Okay, x is the position of the... I need to tell you which particle...
Time is t. What is that?
Oh, this is time.
X
So this is space.
This is x. Space is x.
Yes, no, x is not the physical value of this position. X just denotes, you see, in the usual random variables, all I need to tell you is in which generation you are, because in each generation there is one and only one particle. So as long as I tell you that, okay, I'm in generation n, you know which particle it is, because there is only one.
I understand.
Yes? Now look at here. If I tell you that, okay, I'm in generation n, in my case n is 2, right? But it's not sufficient if I only tell you that I'm in generation n, because we are 2 to the n. So I need to tell you furthermore which particle I am. So I tell you, okay, I'm the particle called x, in which picture I'm this particle. And if I only tell you that I'm this particle, you still don't know what my position is. I mean, my physical position is, which is represented by this height. V of x is this position.
V is position, okay.
Yes. So V is the spatial position.
And absolute value of x is the...
X is just, you know, I need to use a symbol to denote the particle.
But what is absolute sum over absolute value of x?
Yeah, so I'm summing over the two particles in the first generation.
First generation.
Yes. The absolute value of x is just the generation of x. So in the first generation, I know I have two particles. So I sum over both particles in the first generation, and I sum the value of the exponential minus the branch number. Okay. Of course, I mean, you will get the impression that I'm making your life harder because the writing is a little bit unusual. I think it's a lot easier if you write it as exponential, the v or expectation twice exponential or minus well, actually, I think this is a lot easier, right? Because the value of v for the position for the particles in the third generation according to math is distributed according to the size. So I think it's a lot easier if and the number of terms here is 2. I think it's a lot easier if I write twice the expectation of exponential minus psi. I prefer to write it here because there is some. Is there anything wrong with my introduction? Sorry? Okay. So this is only the first part of my assumption star. You see, for the usual random walk, I have 2 parts of the standard assumption. So I still need a second part of the assumption, which I will write it here. I'm summing again over the 2 particles in the third generation, and not only I care about the value of exponential to minus the branch random walk, but moreover I multiply by the value of branch random walk. And then I assume that this is central. Okay, so I know that some people will find it very, very, very exotic. Why would you prefer to write it here? Do I have some color?
It is a great assumption,
Yes,
yes?
yes. Okay, so of course, I really should not write it this way. I really should write that as twice the expectation of psi times e to the minus psi. I mean, the value of this expectation is quite, because there are 2 terms in this sum, and each variable is distributed as psi times e to the minus psi. So, I hope the assumption is clear. Yes?
Okay.
Yes? Okay, so these are my assumptions actually. So for the usual random walk, under the standard assumption, we know that there were a lot of universality results, such as, for example, central limit theorem, which tells you that if you look at this random walk at the nth step divided by square root of n, then it converges weakly to the standard Gaussian law. It turns out that for the branching random walk, something similar happens as well, and this standard assumption, which I write it here. So first, let me recall some historical results.
So, could you explain us why
Yes.
particle can give only 2 particles?
Yes, this, because it's just an example. I want to give you the simplest example. So in my example, there are only 2, so that's why you have 2 here and 2 there. Actually, that's why I prefer to write here. Then you see that I actually don't need to assume that there are only 2 particles. You can have a random number. You can even have an infinite number of particles. It's still true. But I think I prefer to stay with my example so that at least the model will be clear, right?
and the positions of particles of first generation,
Yes.
they are independent
Yes, yes.
in general case.
Yes, they are. Actually, in the general case, I even don't need
All this, okay.
I don't need, neither they are identically distributed nor independent, but I don't want to get into such technical details. I prefer that we stay with this very simple example. Each time you are split into two and all the displacements are independent and identically distributed according to a certain law which I call psi. Then I think at least for this example, everything will be perfectly clear. I hope so.
And a particle died, no die.
In my case, no particle ever dies. Everybody gives birth to two particles and so on. And actually, I can allow my particle to die as well. So the result will be very general, but the result I'm going to write on blackboard looks a little bit special, but that's a personal choice. Yes? Okay. So I think the first important result was obtained in the 70s by King and later by Dickens. And then, from now on, I will always assume the assumption star. They prove that if you assume the two parts of the assumption star, then if you look at the minimum position in the nth generation, so let me remind you that V is my branching random walk. I take the minimum value of branching random walk in the nth generation. So here there are 2 to the n particles, right? So in my picture, I look at the minimum value that in my picture n is 2. So there are 4 values and the minimum value of this guy, which is negative in this picture, right? And it turns out that it goes sublinearly. So divided by n, it goes to 0, almost surely. Which is not exactly a surprise in the sense that the corresponding result for the usual random walk is just Kolmogorov's strong law of large numbers, saying that under such assumptions, the random walk divided by n just goes to the expectation, which is by assumption 0. Yes, you don't even need to assume the second moment, and which is something is again true. This is the corresponding law of large numbers for branching random walk. Okay, so on the other hand, it means that if sublinearly, probably you want to replace this n by something smaller, and you want to get a non-degenerate limit. And this was done by. Is there anything?
It's a question because
Yes.
V is you consider minimum of random walks, right?
Yes.
Why if it is divided by n, why does it go to 0?
That's because of the assumptions. Usually, without this assumption, you have just a constant, and this constant depends on the distribution of psi. Just in the Kolmogorov strong law of large numbers, if you only look at the sum over the first n random variables divided by n, usually all you can say is that it goes to the expectation of psi 1. But there's no reason why it is 0. But if you assume furthermore that expectation 0, then it goes to 0, right? Here is usually there is a constant here. But under assumption star, the two parts of the assumption give me the numerical value of this limit, which turns out to be 0. I hope I have answered your question. Well, okay. Okay, so that was the first part I wanted to tell you. And the second part, a couple of years later, Dickens was interested also about the minimum value, but without this normalization. It's not, I guess, it's not that obvious that actually it goes to plus infinite. question, the branching random walk is transient to the plus infinity. It means that my picture actually is wrong if n is very large, because actually everybody goes to plus infinity, but sublinearly. When the minimum value goes to plus infinity sublinearly. So now you have something which goes to infinity, but which goes to infinity sublinearly. Of course, the natural question is at which rate. Yes? And in the 1990s, so now I'm going to remove everything here. In the 1990s, this question was addressed too by Doklad, and he got something very interesting. You see, what I'm doing is just the corresponding thing for branching random walk. For usual random walk, this first part is law of large numbers, and if it goes to infinite sublinearly, central limit theorem tells you that the magnitude order is square root of n. So you would ask yourself, is there anything similar happening here? And the answer is surprisingly no. So, Doklad will look at the minimum value of branching random walk at the nth step. He proved that, unlike in the central limit theorem, you don't have square root normalization. It's at most log n. So the upper limit is finite. So at that time, it was very surprising. So mathematics was able to prove that if you normalize divide by log n, then it's bounded by a constant. The value of this constant depends a priori on the law of the psi. So 20 years ago, the result was considered as a kind of surprise because it rules out the usual form of central limit theorem, because usually one would try to guess that divided by square root of n, it would go to something. Of course, it could not go to standard Gaussian distribution because I know that it's plus infinity, right? Okay, so let me announce.
Sorry, I don't understand exactly.
Yes?
P of x can have only positive values or
No, it goes to plus infinity, but for small value of n, for example, if my picture n is 2, it's possible that it's yes. Okay, I really should write a second line. I would like to make some color. These two, you see, implies you could give this as an exercise to your undergraduate students. These two imply that the expectation of psi is strictly positive. That's Jensen's inequality. It could be infinite, nothing guarantees that it's finite. Okay? You could give it as a simple exercise of Jensen's.
It's two conditions.
Sorry? Yeah, the star actually, there are two parts of the condition, just like the usual assumption. There are two parts, expectation is 0 and variance is 1, right? So, I mean, the only difference is that, okay, my writing looks a little bit more complicated, but from a mathematical point of view, nothing is very new. I mean, it's just an imitation of the usual assumption for usual random walk. Okay, so now maybe let me announce my first theorem. There will be two. So under the standard assumption, I still need some more inscrutability condition, which I guess nobody cares about the exact form. I need to assume that some things are integrable. Okay. Then I know that this minimum value divided by log n, there is convergence to a numerical constant. And this is a very nice numerical constant. It's 3/2. So if you admit that this is true, then you will agree with me that this condition is a good condition because somehow it tells you that under this condition, then the law of psi doesn't matter at all because each time at the end you always get 3/2, just like the usual central limit theorem telling you that as long as you assume zero mean and variance for 1, then after normalization you always get the standard Gaussian law, nothing else. Yes? So here is a simple universality result under this standard assumption plus this integrability condition. If I have time, I'm going to say some words at the end about the integrability condition, but I'm afraid that's a little bit slow, so probably I won't have time to give you details about that. So this is the convergence in probability, and of course, which is already stronger than the usual central limit theorem, because usual central limit theorem tells you that you have weak convergence but no convergence in probability. Here we already have convergence in probability, but if you are very, very ambitious, you can always ask, can you say more about that? The answer is no. So if you look at the almost sure convergence, then there are some fluctuations. So if I look at the upper limit or the lower limit when n goes to infinity, it turns out that the upper limit has a very nice constant, the same 3/2, but along another subsequence, the lower limit is just 1/2. Almost sure. So this is more or less the analog of the so-called law of the iterative logarithm for branch random walk, except that you don't have iterative.
Sorry. What is the difference in the upper line? You say that in probability,
yes, yes.
It's
an almost sure convergence.
And then they say in almost sure,
yes.
converge to the
along one of the subsequence. Along
subsequence.
Yes. So there are kind of special sequences along which you can get the biggest possible limit is 3/2 and the smallest possible limit is 1/2. But in probability, whatever sequence you take is just 3/2. So there is no contradiction, but it shows you that, okay, they not only prove this convergence in probability, and moreover, they will also prove that the expectation of this guy also converges to 3/2, and they were even able to estimate some deviation probability. So the probability that the difference between this guy and the expectation is greater than something, then they prove that it's at most exponential. So they have stronger estimates than what's written here. But you can still say more than that. The paper is not published yet, but it was posted on arXiv. It says that if you assume something more than the minimum, you remove 3/2 of log n, it also converges weakly in distribution to some non-degenerate limits. Of course, if you assume that this is true, then you divide by log n, and then you get this.
The branch mechanism is more general.
Everything actually is more general. What I'm announcing is just a special example so that you don't need to care about the exact assumption and so on. But everything I'm telling about is general. That's why I prefer to write the assumption in this way instead of saying twice the expectation of e to the minus psi. And that's not all. Actually,
Just a question.
yes?
Is the limit is it specific for every branching mechanism? This limit?
No, not at all. It's a universal observation.
This was the last one. The law, the limit law of this difference.
Yes.
No.
If every time I need to assume this one.
Yes, it's not this limit, yes.
Yes.
Medium minus.
The limit. that depends on the law of psi. Yeah, this non-degenerate limit is not universal. It depends on the distribution of branching random walks. Yeah, so it's not that universal, I agree. Yeah. Okay, but I think it's a wonderful result, right? And it's not cool. Okay, and all this actually, these two parts, so this one plus that one, is known to Gramson. Gramson, I think at the beginning was his PhD. He knew all that, this and that, he knew that for branching random motion. But of course you will argue that, okay, branching random motion is a little bit special because everything is random motion, so okay, you can do some hard computation. That's what Gramson did using a Feynman-Katz formula, and he was able to do all the computation. The second paper is very long. It's published in the series of the AM's memoir, so it has more than 100 pages to prove this result. So for branching, random motion is correct. Actually, I'm coming back to say a few words about this branching random motion story. So for the moment, this is the end of the statement of my first theorem. So I wish to say some words about the second one. So maybe I should erase some review slides, right? So to motivate the second part, let me introduce a new quantity. I'm summing over all the particles in the nth generation. So in this sum, there are 2 to the nth terms, e to the minus b of x, right? Okay, we have already seen something similar for n equal to 1. So under my assumption star, I see that Wn is just a martingale. I don't even need the second part. Even the first part will give me a martingale. That's easy. And this martingale actually has a name. It's called additive martingale. Because, okay, it's not for a deep reason, because it's sum of them. Well, so usually people call it additive martingale. And moreover, it's positive. So a positive martingale, we know that it automatically converges. So almost surely I know that it converges to some. The limit, I'll write it as W infinity. It turns out that so begins in 78. He said that the limit is 0. So it's not uniformly integrable because the limit is degenerate. Okay, so a question, but Bibius waited, let me see, 27 years, and he needed a second person to ask you this question. If you meet him, you should ask him why. So he waited more than 20 years to ask what about the rate at which, since we know that it goes to 0, of course, you want to know how it goes to 0. Yeah? And this time I think I'm going to spend, I know I'm late, I'm going to spend 5 minutes more, not more, to tell you a historical story about Henry McKean. Here. So the study of branching process, of course, has a a long history. And the study of branching random walk and the branching Brownian motion, somehow even in the 60s, there are some activities made by a group of very strong mathematicians in Japan, so including big names like Watanabe, Nagasawa. But it became really popular only in the 70s after a paper published by McKean. And McKean, I think the main interest is that he was able to connect branching Brownian motion with a partial differential equation called FKPP, or sometimes simply called KPP. F is for Fisher. I can write his name without any problem, but I have troubles with the KPP because each time I write the names down, then I commit a mistake somewhere. So we are in Moscow, so I prefer not write Russian names with the wrong spellings. So K is for Kolmogorov, P is for Karpsky, and the second P is for Piskunov. Yes. But each time I try to write down the names, I know that there is at least one mistake. Sometimes there are several mistakes. So I prefer not to write down what the exact names are, KPP. So Kolmogorov, Pekovsky, and Piskunov. F is for Fisher. So McKean actually used branching Brownian motion to contract explicitly a so-called traveling wave solution to the FKPP equation. It's not very complicated, but I don't think it's the aim of my talk to give you the exact representation because I'm not going to use it anyway. But somehow this was made the people feeling very excited about the study of branching Brownian motion and of branching random walk. And a few months later, McKean published an error term. He said, oh, someone pointed out, his name is Dr. Hong-song. He said that Dr. Hong-song pointed out that there was a flaw in my proof. So since I want to tell you where the flaw was exactly, so I write just one line. McKean used this representation in terms of the branching Brownian motion e to the minus x times w. Well, this notation was different actually, but in our notation is this. Here, capital C is just an unimportant finite and positive constant. This is as a function of x. And W infinite is the limit of our additive martingale. So McKean said that since my additive martingale is positive, well, it's strictly positive, so the limit is positive. So I use this one to represent the traveling wave solution of the FKPP solution. But the trouble is that it's possible that even if the martingale itself is strictly positive, it's possible that the limit is 0. So in case the limit is 0, then the argument of McKean is wrong. And we know that the limit, unfortunately in this case, is 0, which means that there is a problem with the proof of McKean. So just a few months later, McKean wrote that, okay, sorry, there is a problem with my arguments. And a few years later, Liley and Selke, they said, okay, now that we know that there is a problem with the contraction by McKean, now we suggest something to replace this contraction. I'm going to use a different representation. And they use something which is very similar, except that instead of this random variable, non-negative random variable, which turns out to be 0, they use something which is strictly positive. This random variable d infinity, they prove that it's strictly positive. So now let me tell you what this strictly positive random variable is, which we call d infinity. So let me introduce a second martingale. I sum over all the 2 to the n particles in the nth generation. It looks very much alike the additive martingale, except that I multiply the exponential minus v by the value of it. Okay. Again, thanks to my assumption star under under my assumptions with the 2 parts, I realize that d also is a martingale. So psi implies that d is a martingale. And this martingale also has a name called derivative martingale. It's called derivative because somehow this is formally, this is, well, with the minus sign, the derivative with respect to d.
E tends to infinity help us to have a positive limit.
Yes, that's a good point, because we know a priori that everything will be positive, so it really doesn't matter when n is sufficiently large. So this is proved by Wiggins and Cipriano. I never remember which year is which. It's 2004. So that's a problem when you write a lot of papers. It's very hard for the reader to remember which year you wrote which paper. So they prove that the derivative martingale also converges almost surely to something which they call the infinite. And what's more important is that this guy is strictly positive. And this has exactly the same contribution as that. Okay, so I just told you a few historical things. Now let me state my second result. Here is our second result. Under the assumption, okay, everything is under assumption star, of course. Under assumption star, if I look at the additive martingale, we know that it goes to 0, but if I multiply by something very large, square root of n, it turns out that it converges in probability to a very nice limit, which is square root of 2 divided by pi sigma square d infinity. And this d infinity is exactly the same d infinity as the one before. In other words, somehow the additive martingale, somehow if you normalize properly, then it goes to the same limit as the derivative martingale if you don't care about the constant. Okay, I will write it the constant sigma square. This is defined as expectation over the particles in the first generation, the square of v times e to the minus of v. And what I didn't write here, I also need some integrability condition. Anyway, I always need some additional integrability condition to ensure that this guy is finite. Yeah? So if you don't like my writing, you can see that this is exactly the same as twice expectation of psi squared into the minus 6. Okay. So if you don't care about the constant, then it's the same limit. So actually, of course, now we know that Makin did commit a mistake, but actually this mistake was not that, it was not that wrong. Actually, as long as you do a different normalization, then everything in the argument of Makin goes through. So a posteriori, the mistake actually can be easily fixed without much trouble. because now we know that actually these two martingales asymptotically they go to the same limit. Of course, if you are very ambitious, you can still ask the same question, whether this convergence in probability can be replaced by almost sure. Unfortunately, the answer is no. So convergence in probability is what you can say the most. We were not able to prove, to get the exact rate, but recently, my co-author Yuan Hu, so the paper is going to be published in a couple of years, he was able even to characterize the rate at which it goes to infinity. So that's something very, very, very strong. Unfortunately, I don't know anything about what how he managed to prove that. Okay, so I have a few minutes left. I want to say some words about how I managed to prove things for branching random walk. So I'll give you the main tool. Actually, it's the only general tool I know for branching random walk. I don't know anything else. So I cut this from Biglin's paper. And this paper was written, that's another one, in 1998, and they tell you the following. If you look at the expectation of sum over all the particles in the given generation, the n generation, and this will be correct for all n. Okay? And I sum a measurable function, so the energy is a measurable function. Let's say G non-negative so that I will have no problem with the expectation. Here, in principle, what I do care about is a function of the value of the branching random walk. But actually, I can say more. I can even keep track of all the history of the branching random walk. So actually, I'll take from the beginning until the end. Okay, so now I need to say one word about what I mean by v of x1 and v of xn. So I will write it somewhere on the blackboard. Maybe here. So what I mean by v of x1, v of x2. So this was my original picture. At the beginning, I only have one particle as original. And time one, I have two particles. And then I have four particles, and I make a further in the last picture. And I stop here. So this is my generation n. In my case, n is 3. Yes? I'm summing over all the 2 to the n particles in the nth generation, which I call generically x. Let's say this guy. So this particle is called x. Its physical position is v of x, right? So since we are in generation n, so okay. His father, I will call it xn minus 1. His grandfather, I will call it xn minus 2, and so on. And this is the origin, the root of everyone, which I call x0. So this is x0, x1, x2, and until x is xn. If x is in the generation. Yeah? So I hope the definition of xi is clear. Somehow I look at not only the value of the branching random walk x of a given particle in the nth generation, but I keep track of all its paths as well. So I take whatever function which is given, which I call g, of all the entire past of this particle x, v of x1 until v of xn. Yes? And I need to sum over all the particles in a given generation. And it turns out that there is a very simple expression for this expectation. It's just expectation of a usual random walk. So Si minus Si minus 1, they are ID random variables. So on the right hand side, the Si is just a usual random walk. Well, S0 is the factor. So you see at the beginning I have a whole bunch of random walks because along each branch I have a random walk. Yeah. So in this sum, sorry?
Let's multiply something like number. Parts, yes, because say G is equal to 1.
Yes, sure. That's a very good point. It's not exactly true. I need to put some density. And the density is very simple. It's e to the terminal value. That's it. Well, for the moment it's useless because I didn't tell you what the new random walk Si is. So I need to tell you the law of Si. So where the law of Hi is such that I take the expectation of whatever measurable function of Si is, let's say h of Si. So whatever measurable function, let's say non-negative, then the expectation of a given measurable function of Si is defined as expectation over some, oops, maybe I should write here. This line I'm going to write it on the right hand side. Expectation of whatever measurable function of S1 is expectation over sum of the two particles in the first generation of h of the value of the branching random walk times exponential to minus v of x. That gives you the law of S1 because you take h to be the indicator function of half line and it gives you the
Well, it's an assumption. It's an assumption. What is it?
That the solution of S1 is defined.
This is to give you the law of S1, right? I need to give you what's the new random walk.
This sounds like grammar transformation.
It is. You are absolutely right. Yes. So you see on the left-hand side, I have a whole bunch of random walks. The number of random walks is exponential, 2 to the n. But these random walks are somehow correlated because lots of them share a few common lines. Between this and that, for example, is common until here. Then they set, right? So these are correlated random walks. So somehow that's very hard to study when you have a very complicated dependent structure. Whereas on the right-hand side, you only have just one single random walk. So everything is perfect. And if you only have one single random walk, I guess everybody will feel very happy. Yeah? I need to tell you one word about why this is such a formula is true. Actually, this is not exactly due to Biggins and Cipriano. Actually, it's known in the 70s, and also it has been used by all kinds of people in the 80s, 90s. Each time I get the impression that people rediscover something which was already known in the literature, but written in a different way. So as far as I know, the first persons having such ideas, they didn't write it exactly this way. I would say it's Bingyang and Zhongli in 74 or 5. And Kian and Bahir published in 76. But if you check on both papers, if you check the received data of the paper, then you realize that the two papers were received more or less at the same time. So it means that they would done more or less simultaneously, but done in a different way. So now I need to tell you in one word why this is true. You can also give it as an exercise to your undergraduate students as long as they know what conditional expectation is. I'm going to prove it in one line by induction in N. For n equal to 1, it's just a definition of the law of S1 method. So that's my the first half of my one-line proof. The second line is assuming that it's correct for n, and now you need to prove that it's correct for n plus 1. All you need to do when you sum over everything in the generation n plus 1, you just condition on what happens in let's say, in the first generation. And then you have two independent branches of the branch random walk, and you look at what happens in the nth generation. You use just induction assumption and in relations. Still something, the same thing holds true. So that's the end of the proof. So, I mean, the formula itself, there is nothing very special, except that now, I guess, at this time, everybody will be convinced why my assumption looks very natural, because the second part of the assumption tells you that expectation of S1 is 0. So this is exactly what you said, that it's a kind of Cramer's transform which changed the value of the drift, because let me remind you that along each of the branches we have a positive drift. Whereas in this new random walk on the right-hand side, I only have 1, but the drift is 0. It's mean 0. Yes? So at the beginning, I have a whole bunch of positive drifted random walks, but somehow I managed to make appear just one single random walk, which is driftless. Okay. Now that you have such a general tool, somehow you can always manage to reduce your task to the study of one single random walk which has mean 0. So I guess that part I don't need to tell you very much about how people do things like that. Thank you very much.
Пожалуйста, вопросы?
About the, what is known, or how much is known about the V of the distribution of random field in some sense. If you
Which
take,
field?
okay, you consider nth generation,
Yes.
and you consider all the points in this generation. Can you say something about the structure of this?
Yeah, you see, it's very different. Typically, the positions are at order n, because along each given branch, there is a positive drift. I erase it, because usually, if you close your eyes, you just take one point, then the value of v at this point in the nth generation is, roughly speaking, a constant times n.
So the question is, you are speaking about the minimum.
Yes, because it's a very special, it's an extreme value actually.
Yes, right. Can you say something about the maximum?
The distribution
the maximum
between
value is-
minimum and
sorry?
maximum, which is the empirical distribution between minimum and maximum.
Actually, if you study the empirical distribution, then you are not going to see any more all these minimal values, because typically a value is a constant times. The constant actually is expectation of psi. That's law of large numbers. So typically, you will see that most of particles are in this condition. So if you look at the empirical distribution, then you are not going to see all these 3/2 times log n particles, because there are only very, very few of them. They are very strange. If I will come back to your original question, if you want to study the max, then that's easy. All you need to know is to replace psi by minus psi. Yes, and then you need to make a different linear transformation to
Okay, can you say something about the second largest
yes. That's also true. That's a very good question as well. it's done by two different teams. I'll give you only the name of the first teams. It's again. I'm glad that you asked the question first. Bouvier and Kissler. So they studied the empirical distribution, but only in the neighborhood of the minimum value. So you only see a finite number of particles. And then they prove that actually view from the minimum condition, then the empirical